Alright guys, welcome to my presentation, and today we're going to be talking about conjugate acid-base pairs, and then we're going to dive into a relatively new real-world application of a conjugate acid-base pair. So to start us off, what are conjugate acid-base pairs? And we're going to be using this diagram to help explain. So, a conjugate acid-base pair consists of two substances that differ only by one proton. So, you'll see this HA and this A, they differ by only one proton. Likewise, this B differs from this HB by only one proton. The A doesn't mean anything really. It doesn't mean that it's an element. There's no A element because it doesn't matter really. It just matters that there's a proton here, no proton here. Likewise with the B is not, well, B is an element, but it's not boron. And so what matters is that this B doesn't have an H to it, and this one does. So HA and A are conjugate acid-base pairs, and B and HB are conjugate acid-base pairs. But now we got to identify which one's the conjugate acid, which one's the conjugate base. Well, a conjugate acid is formed when a proton is added to a base. So we see here, this proton is being added to this base, producing HB. This would be the conjugate acid, this would be the conjugate base. Conjugate base is formed when a proton is removed from an acid. So, proton is leaving A, forming A minus. Thus, this would be the conjugate base. This would be the conjugate acid. Now, for a couple of examples, there's going to be 3 examples, and your job is to identify all conjugate acid-base pairs and then specify which is the conjugate acid and which is the conjugate base. So, first one, pause it, try it out. I'm going to take over. We see that these two molecules differ by only one proton, and these two molecules only differ by one proton. So we would say that these two are conjugate acid-base pairs, and these two are conjugate acid-base pairs. Now it's time to identify which one's the conjugate acid, which one's the conjugate base. Well, this one has one proton, this one doesn't. This one must be the conjugate acid, this one must be the conjugate base. Likewise, this has a proton, this one doesn't. This one must be the conjugate acid, this one must be the conjugate base. Pause it and try it out. We see differs by only one proton in each of these. This one has a proton, this one doesn't. This one has one proton, this one has 2. And that's where things get a little bit tricky. It doesn't mean, one has to have a proton and one doesn't, because we see here, this one has one proton, this one doesn't. This one has 2. Also, just because something is a conjugate base doesn't mean it is a base. So HSO4 is the conjugate base to H2SO4, but HSO4 isn't a base. We know that's an acid because it has this proton, and it would donate this proton in solution. But since it only has 1 compared to the 2, that's the conjugate acid. This is the conjugate base. This one has a proton, this one doesn't. This one's a conjugate acid, this one's a conjugate base. Sorry, that's a really bad beat. So is that, but whatever. Alright, last one. Pause that, try it out. So, we see these two molecules differ from one proton, and these two molecules differ by only one proton. Again, it doesn't matter with how many protons it has, or if it's an acid or if it's a base. These are both acids, right? What matters is this has 3, this has 2. This would be the conjugate acid, this would be the conjugate base. Water has 2 protons, hydronium has 3, this would be the conjugate acid, this would be the conjugate base. Alright, so now we can jump into our little example of a real-world application by looking at the hypochlorous acid and the hypochlorite conjugate acid-base pair. Before we do that, we have to figure out how to actually get this hypochlorite. We do this by putting sodium hypochlorite into a solution of water. It's going to break down into hypochlorite, some hydroxides, some protons, and some sodium ions. So where do we get this sodium hypochlorite? Well, sodium hypochlorite can be produced by bubbling chlorine gas into sodium hydroxide, or we found a newer and more efficient way of doing this, and it's actually by the electrolysis of a solution containing water and sodium chloride. And I'm not going to jump into the details of that because electrolysis, we know, is Module 12 talk, electrochemistry. But all you really need to know is that we have this sodium hypochlorite. It's going to break down and form this hypochlorite. And this is what we're going to look at. So here's the equation of reaction. We have this hypochlorite in a solution of water. It's going to form hypochlorous acid and some hydroxide. The Ka of this is 3.5 times 10 to the negative 8. We take the negative log of that. pKa would be 7.46. Since this would be the conjugate acid because it has an H and this one doesn't, the pKa actually represents the direction of that way. So the pKb would be representing this way of the equation. And the pKb would just be 14 minus 7.46, so 6.54. So we're going to be looking at this hypochlorous acid for the rest of the presentation. Here's what it looks like. It's just a hydrogen, an oxygen, and a chloride. And so why do we care about this hypochlorous acid? Well, it is an extremely good disinfectant. And actually, we literally spray it on people right now because of COVID-19. I don't know where this is, but what they're doing is they're just, before people enter, a store or wherever, they're literally spraying hypochlorous acid onto people to kill any COVID-19 if it were to be on their skin or coat or suitcase or whatever it may be. And so, why is hypochlorous acid such an effective disinfectant? Well, it's an extremely good oxidizing agent, and that should make sense to you because we have an oxygen and a chlorine. These are both very electronegative, so they're going to be sucking electrons from anything they can come close to, really. And so here's the mechanism. So this represents a pathogenic cell, so a bacteria or a virus or whatever it may be. These hypochlorous acids are small. They're relatively small. They're not tiny, but they're relatively small, and they're uncharged, so they can just diffuse right through their cell membranes. And once they're in here, they have a whole lot of mechanisms. So they can stop replication, they can stop the formation of ATP, they can inhibit protein synthesis, inhibit translation, or if the protein is ended up being formed, translation does go through, well, this hypochlorous acid can just break down the protein. The hypochlorous acid can also sit on the cell wall or the cell membrane and just destroy the cell membrane. And they can do all of these because it's just stripping electrons from DNA, from ATP, from the cell membrane. It's just, from the protein, it's just stripping electrons from them, breaking them down, and ultimately it's going to kill the cell. What is also cool about hypochlorous acid and why it's becoming such a popular disinfectant is it is 100% safe for humans. It's chemical free, it's non-toxic, and it's all natural. So it's going to just break down into protons, oxygens, and some chloride ions. And we obviously know that those are throughout our entire body, so it really doesn't matter if it breaks down. And so it's much safer than other chloride-containing disinfectants, such as sodium hypochlorite, which we talked about earlier. So sodium hypochlorite, along with many other chloride-containing disinfectants, if they encounter an acid, chloride gas is going to be produced. And why is that bad? Well, chloride gas is very, very toxic. And so, for example, if we tried to spray ourselves with sodium hypochlorite, well, if we ingested a little bit or if we inhaled a little bit, well, we know our stomach is completely full of acid, right? So that would not be good because then a bunch of chloride gas would be formed and we would probably die. And what's interesting, and we are thankful for it, is we literally copied our immune system. So this is a white blood cell. Let's pretend this would be encased in a white blood cell, more specifically a neutrophil. What happens is they take oxygen gas and they reduce it through a series of reactions and enzymes to form hypochlorous acid. And white blood cells are also able to do a process called phagocytosis, where they engulf the pathogen or the bacteria or the virus or whatever it is. Once the bacteria or pathogen or whatever it is inside the cell, the white blood cell, well, then these hydrochloric acid molecules go to it and do exactly what I just talked about in the last slide. Just go in and just absolutely eat the cell inside out and from the outside, destroys the cell membrane as well. It just completely demolishes them. So that's why it's a really good disinfectant. It doesn't hurt us. We can ingest it. It won't kill us. And then ultimately, it'll kill the pathogen and completely clean whatever surface or whatever you are cleaning. And that's all I've got for you guys today. I hope you learned something. I hope you guys are familiar with conjugate acid-base pairs, how to determine if it is a conjugate acid-base pair, how to determine which one's the conjugate acid, which one's the conjugate base. And I also hope that you can are more familiar with hypochlorous acid and how we're starting to use it more and how we literally copied it just from our immune system. Thanks, guys.